So, show of hands, who would rather just listen to tunes for the next hour rather than to listen to us talk? Anybody?
There was a
Anybody?
hand over there.
Where? Get out. Just kidding, you can stay. Well, thanks for coming. Show of hands, who caught our session right before lunch? Okay, who didn't? I should have asked who didn't. Okay, all right. So I'm going to do a little review for both of you. First of all, this is Katharine Beaumont. My name is James Weaver. I work for Pivotal. She works for Voxed. She's a mathematician and a developer. I'm just a developer. And she's going to introduce herself.
Hello, as you've heard, I'm Katharine. I'm sorry for the people who attended the first session, you've already heard my life story. But I work for Voxed. Voxed is behind the Voxed Days conference. I write content for the Voxed website. I interview speakers. The website actually accepts contributions, so if any of you feel like you're making my life easier and sending me articles, I'd be very grateful.
And I'm James Weaver, and I've been a Java developer forever, written several Java books, J2E or JEE, Raspberry Pi was my latest book, JavaFX, things like that. And I played this clip earlier. I'm not going to play it now, but this person is pretty influential. We've both taken Andrew's course. He's one of the founders of Coursera, and does a great learning or machine learning program or curriculum on Coursera. He's also the chief scientist of Baidu, which is a Chinese technology company, and is just kind of a luminary in machine learning, as are a lot of other people like Jan LeCun, Facebook, and some others. But these slides are available online, and so if you come across this one, it would be good to actually take that course. So machine learning is good for lots of things that you've heard about these days, like self-driving cars, being able to generate image descriptions, what's going on in this image, and supervised learning. There's three types, as most of you know now, three types of machine learning. Can somebody shout out the first one? It's right there on the slide. Okay. Somebody say supervised learning. Ready? Okay, good. What's the next one? Unsupervised learning. So supervised learning, there's the house price prediction, where we're given a feature or more than one feature, and we're trying to predict then some outcome. In this case, we're trying to given enough data samples, we're trying to predict for a given house price and maybe a number of bedrooms or whatever, what the price of the house would be. So then there's unsupervised learning, in which you're trying to find structure in data, like clustering or something. And then there is reinforcement learning, in which you reward, you have an agent that you're rewarding as it goes through and is successful in learning something. You're giving it rewards for being successful. So AlphaGo, which is a Google DeepMind thing where they had a championship and beat the leading Go player. So we're going to dive into supervised learning, and so a lot of times supervised learning, you're classifying things. So this is the example where you've got a data set that has dimensions of an iris plant, and then three different species that it could be. And so you're teaching, based upon that data set, you're teaching the machine learning algorithm how to classify it by giving it data points. So the data points are the data set which has the features of the petal length and width, sepal length and width, and then what species they are. And then the machine learning algorithm then is in this case an artificial neural network, is bringing those in and adjusting its internal weights to represent and to be able to link up, just like your brain does. When it sees an image of something, it can tell what it is. It's linking up looking at a particular dimensions of an iris flower, and then figuring out what it is. And that's the secret sauce in what we'll be doing now, is we're going to be talking about how does a network learn, specifically an artificial neural network. So, as I said this morning, if we have 4 features, we've got 4 dimensions. There's 4 features, length, width of the sepal and petal, and we have to be able to distinguish between the boundaries of those in 4 different dimensions to be able to successfully classify them. And so, again, catching up a little bit, the brain artificial neural networks are modeled after the brain, where you've got inputs and outputs and neuron and synapses. Those are modeled in artificial neural networks. And then I'm just going to show you one other thing that you might have seen this morning, and that is this application where I wrote an application that helped me kind of understand what's going on inside of a neural network. And it's written in Java and Spring and Angular 2. And so I'm just going to go ahead and do the iris data set one, and so we can see the neural network. If I click on iris flower, we can see it learning. We can see the input layer here, which is the 4 features that we're learning. We can see the different hidden layers, and we've got these are called neurons, but they also have activations, and Katharine's going to talk about what activations are. These happen to be hyperbolic tangent activations. And then here we have an output layer which has softmax activations. Softmax activations then are guaranteed to add up to 1. So a probability, for example, that it'll give you a probability if I type in a 5 centimeter length for a sepal and a 2 centimeter width, and then a 2 centimeter length of a petal and a 2 centimeter width, and I hit predict, then we see that there's a 72% chance that it is a virginica, but 28% chance that it's a versicolor. But notice those add up to 1, the probability of 1. So softmax layer, if I use softmax activation functions at the last layer, it's guaranteed to add up to 1, and so that's really good for classification problems. And now, anytime you see this dog, we call this math dog. And so anytime you see this, it's time to get into some math, some intuition and math about what we just talked about, and then kind of looking ahead. So Katharine, please illuminate.
Okay, so one of the key things behind neural networks, we saw the input features there, the sepal length and different features, is what if we can work out what those features are? So in your brain, you might look at a chair, but you don't know how your brain works, that it goes, okay, it's the shape of a chair. It's black. I don't know what else makes it a chair. We don't consciously decide how we make these decisions. So the idea behind neural networks is, can we mimic the way the brain works and magically work out what the features are? So, thank you. So, for example, these are the input features again from the house price example we saw this morning. Can we predict the price of a house based on the size in square feet and maybe the number of bedrooms? And it might not be a simple linear correlation, it might be more complicated. Or it might be that there's a lot more to it than just bedrooms. It might be garages and garden sizes or something as well. So just a reminder of this hypothesis from this morning. We're going to work out what our hypothesis is by combining these theta values. Theta is just a way of saying this is a weight. So imagine we have the size in square feet, and it turns out that the price is 5 times the size in square feet. And that number 5, is the weight that we assign to it. It's how much do we scale this feature to get the answer. So those theta values represent weights. So if we're trying to model this in a neural network way, those x1 and x2 there, size in square feet, number of bedrooms, are inputs coming into this neuron here, where some kind of calculation happens and we get our output. So this is the idea that in the brain you might see something visually and that's your input. Something magic happens in your brain and your brain goes, that's a chair. So in the very, very basic explanation, you get an input, which is a spike of activity from a synapse. And that charges something in the neuron. And when there's enough charge, something goes out and it goes on to the next neuron. Synapses are actually really simple and really slow. Well, not really simple, sorry. They're really small and really slow. But they can adapt. They can adapt how much charge they send into the neurons. And they can adapt how much charge, I think they can adapt how much charge they accept as well. So it's not simple information going in the neurons in your brain. It's that the synapses can control how much. So we want to mimic that with some kind of adaptive network. And it's not that simple. You've got 86 billion neurons in your brain. So we're going to look at a really simple example with like 3 or something like that. So here are input units. We've got our neuron and we've got our output. So we've got inputs coming in. This is our charge. Some kind of thing is going to happen in the neuron that's going to activate them and send a charge out, which is going to be the answer. So the crucial thing is that we're going to somehow activate it. And we don't actually know how neurons do that, but we know that the charge, we can really simply describe the charge as a 1 or a 0. Is something being output or is nothing being output? But actually, it's that there are different amounts of output. So one of the big problems with neural networks is how do we describe what's happening in a neuron and transfer it to a computer situation? So there are a few different things. You saw the tangent, you saw the softmax function. We're going to talk about the sigmoid function. Ways of mapping this charge and saying, what do we think this charge is? Is it a real number? Is it a 1 or a 0? How do you describe that spike of activity? So that's one of the big problems with neural networks. Your brain is so complicated, how can we possibly put it in computational terms? But we're going to try. So this is a really basic look at what a simple neural network might look like. So we've got our input layers, we've got a bias unit. We saw a bias unit this morning, the y-intercept. I don't know if that helps you understand at all. Probably not. And then we've got x1, size in square feet, x2, bedrooms. This hidden layer is going to try and learn some features, because maybe it's not the size in square feet, maybe it's not the bedrooms, maybe there's a complicated relationship between them. We call it a hidden layer because the idea is that we don't know what's happening. From your input to your output, we don't properly know how it makes these decisions. So it's hidden from us because we're not going to tell it what to do. We're just going to feed it information in and let it train itself. The hidden layer.
By the way, I forgot to mention that we do accept questions during the talk, but to keep on track, we may give abbreviated answers, or we may say we're going to cover this later, or we may just say, let's take it outside. Well, I mean, not like that. Now let's take it, but you know what I mean, right? Okay. So anyway, I guess there's math talk. So anyway, just to recap a little bit what Katharine said, we have input layers, hidden layers, output layers, synapses, and neurons. Those are also called deep belief networks. Sometimes you'll see DBN instead of artificial network. Yes, question? Okay, the question is, are there always 2 hidden layers? And the answer is no. It could be 1 hidden layer, it could be 20 hidden layers. And those are the number of hidden layers, the number of neurons in various layers, and lots of other configuration parameters. They call those hyperparameters in the context of artificial neural networks. Thanks for your question. Okay, so here's a very simple neural network trained for XOR logic. You're all developers. You all know what XOR is. So I'm going to go ahead and go to this application, which is in the slide. There's a link to the GitHub, by the way, if you wanted to create this application. But I'm going to hit the XOR. And it takes in a 1 or a 0, 1 meaning true, 0 meaning false. It takes 2 of those. And then it's going to output either true or false. So if I put a 1 and a 1 in here, what will the answer be? Will it be true or false that 1 true XOR true? Which one? False. Okay, so predict. And we get 100%, a 1 that it is false. So how did that work? Well, these numbers are responsible for that working as far as the calculations. So we're going to cover what's called the feed-forward calculations and how it came up with, how it got from these features to this classification, and then we'll also be talking about how to train these numbers. That's part of the secret sauce. So with a feed-forward calculations, I'm going to just go through some brute force math with you, and then Katharine will deal with the nuances and kind of things behind it. But what happens is, let's say, for example, I want to compute this neuron here. Then what we do is we multiply the inputs. So here's a 1 and a 0. So those are the inputs. So we multiply its inputs by the weights. So it's 1 times 8.54. That's the weight of the synapse. If you're familiar with directed acyclical graph terms, these are I could call these nodes and edges. Let's say so. So this edge times this node is plus this node times this edge is 8.54. And then I'm going to add the bias. Now that bias is here, so I'm actually subtracting 3.99 and getting 4.55. So in terms of the slope and y-intercept, remember that model with the housing prices, etc., the bias is the y-intercept. It's analogous to the y-intercept. These weights that we put here, the rest of them are kind of analogous to the slope. So we add the bias, and then we use this sigmoid activation function in this particular case, in which we do this calculation. So we take e to the negative whatever this was, add 1, and then take the inverse of that to get 0.99. So that's then the value of this neuron after the activation function has been applied. And then we do the same thing here. And when you run through all those calculations for all of the nodes, then that's what you get. And so now please enlighten us on the nuances.
Oh, so I'm just going to go over what Jim said again, but with some of your favorite theta values. So here we go. So here's the example again of a simple network. So we've just got one hidden layer here. We've got our input layer, and we've just got one output, which is the equivalent of our hypothesis. And all of these pink lines represent the synapses. So they're the data going from one place to another. We're going to collect all of the data in the neuron. We're going to activate it, and then we're going to fire it back out. So to move through the layers, this is the sigmoid activation function. So when we keep mentioning sigmoid, you can imagine it as a function that squashes whatever number we have and fits it in between 0 and 1. So even if we get an output of like 90, that will be close to 1, for example. And if we get an output of like minus 90, we'll get something that's close to 0. So you can think of it as a way of transforming whatever number you get and just squishing it in between 1 and 0. So in order to move forward through the network, I'm just going to show you going from the input to the first unit of the hidden layer. So if you watch this back and you're like, why is that x2, why is that a2, what is she talking about? I've got a handy key here for you to look at. So to get from our inputs to a2, as Jim showed, what we're doing is we're going to times 1 by this first theta value. We're going to times the first input, like the size in square feet, for example, by a different weight. And we're going to times the final one by another weight. We're going to add them all together in this neuron, and then we're going to activate it with, say, for example, the sigmoid activation function. So that's how you get from the input layer to one of these hidden units. If you have a big network, obviously it's more complicated. The idea behind these theta values, if you're thinking, why is she talking about theta, is the concept that we don't know how much each one of those inputs affects the final output. So what you're actually training in the network is these theta values, and what we're going to call here is weights. So that's how we get the first one. And the second one is exactly the same. It's that we've got a different weight now for each synapse. So each synapse has its own weight on it, its own way of controlling it. So we're going to times them together, add them all together to get our second unit of the second layer, A. We're calling it A because we're going to have activated it, but I'm not going to do that here, so don't worry. Okay, if you want to vectorize this, then you can. So
what does vectorize mean?
Oh, sorry, I'm probably using the wrong term anyway. If you want to do it if you want to do this rather than going from example to example, if you write your own program, it's much quicker if you use matrices and vectors. So you can use matrix multiplication to make this a lot computationally faster. And in fact, it's so expensive from a computational point of view to run neural networks that you have to do this if you don't want to be waiting about 5 years for your answer.
Right, so different languages have different libraries for linear algebra, like, for matrix multiplication and things. So like Python has NumPy, Java has libraries for that. So these are all libraries that you don't have to understand all the detail to implement, but you can use the APIs to do matrix multiplication. I should say, I said this this morning, but it's not necessary to understand all this stuff just to do machine learning. There are higher level APIs, but the name of this talk is Machine Learning Exposed. And so we're trying to kind of expose all of the technologies underneath so that as you're using the higher level APIs, you have great intuition and understanding about what's really going on under the covers.
One of the biggest things for me, actually, when I was learning machine learning is just working out how matrix multiplication works and reminding myself. Because if you get the shape of your data wrong, then just errors everywhere. So what we can do is from those, if you remember the first 3 input units going to the 2 hidden units, we had 6 pink lines, 6 synapses. So that matrix there just represents each of those weights going in. So that's 3 of them. And this vector here of x represents bias unit, first input, second input. So size in square feet, bedrooms. And I'm going to gloss over these because I'm sure you don't want to look at them on a Friday afternoon. But if you want to go back and look, then that's how you would do it from a matrix point of view. So we can imagine here we've got the bias, first input, second input going to the first layer there. And the colours correspond to those colours, so you can flick back and through, and the slides are online if you want to have a look at that. And then here again we've got the mappings to the second unit of the hidden layer.
It's straightforward but tedious, which is why we like libraries to do it.
Yeah, this is the thing. In principle, it's very simple because you're just timesing things together and you're adding them up, and then you're performing some function on them, like the activation function. And the thing that makes it not simple is the fact that you might have 50 input units. You might have 3 hidden layers and kind of synapses everywhere. So it very quickly gets very complicated because of the scale. Yes?
It's the first node in the hidden layer. Why is it there again?
Okay, so the question was, what's the first node in the hidden layer? Why is it, what?
Why is it there again? Because it's already in the layer.
Yeah, Catherine, why is it there?
That's a very good question, and I actually took out the slide that explains this, so I regret that now. But if you think back to when we're doing a linear problem, and we're mapping, we're just trying to find a simple linear relationship. I'm going to use my arms. I'm sorry if this looks stupid. So here are the axes, and we just want a line that goes through the data points. And we can change the shape of the line as much as we like, but we might want to shift it a bit to the left so it intercepts y at a different point. So with the sigmoid function, if you remember that it was this S shape, we can change the shape to be steeper or further spread out, but we might want to shift it to the left or the right. So it allows you to manipulate the data a bit more by adding this bias term. And so typically you add a bias term at every layer of the neural network apart from the output layer, where it doesn't make any sense. But part of that's configuration, but it gives you a bit more control over the data. Well, over what's happening to the data.
So I have the sigmoid up there while you were talking, and so you can see by changing the bias, then you're moving the trigger point really right? Is that what you're saying?
You can think of shifting the whole thing maybe over here or over here with the bias term. But if you don't have the bias term, you're just compressing it or stretching it.
Is the small p in the calculation before?
Okay, please repeat the question.
Was it the small p in the calculation before? Do you mean...
It was the b. There was a b in the calculation. Yeah, in the one that I went through. Okay, so we'll move on here.
Okay, so it's quite easy actually. Now we're going to the output layer because we've only got one unit that we're mapping to. So we've only got 3 synapses. So we're just going our friendly bias term, and then we're going the activated results of A2 times this theta value. So just imagine that we've transformed this A2 with a sigmoid function. And then we're doing the same with the final unit, and that should give us our output. And again, here's a vectorized version of the calculation. So you can imagine here, again, we're just going bias term, first hidden unit, second hidden unit, and we're mapping it to the output just with these 3 synapses and these 3 weights. Are there any questions on forward propagation? Yes.
What's the number of input parameters given managed to keep the population?
So the question is, what number of parameters should we use for the input layer and the number of hidden units to have a calculation under 10 seconds? Depends very much, because if you're just calculating one example, then it depends on your laptop but typically what happens is you'll run this through all of your data, so it can take a while. We'd have to play with some different sizes to work out under 10 seconds, but you can do it quite quickly if you use a language like MATLAB. So I do all of my mockups with MATLAB because it's a mathematical programming language. It's optimized for dealing with matrices and vectors. Rather than Java, you'll probably get a much faster result, whereas if you try and code it out in Java, then it might take a while. So it really depends. But one of the reasons why neural networks have grown in popularity, because they've actually been around for a long time, but you might notice now that everybody's talking about them, is because now we've got the computational power to deal with large neural networks. So it's a lot more accessible.
How do you find out the optimal number of hidden layers?
So the question is, how do you find out the optimal number of hidden layers?
I'm going to show you a resource that will help you with that. Yes. Is that okay?
Yeah, absolutely.
Okay, good.
In terms of the cost function, there is a way to work out the cost of a neural network. So for people who didn't come to our first session, the cost function is, can I compare all of what I know to be the right answer with the output that the neural network's given me and find some way of working out the cost? So it's the exact same principle. It's that, taking away what it's predicted that the answer is from the actual answer and summing up those differences. So it's sometimes called the squared error because it's the square of the differences.
Okay, questions on that? We will address the optimization issue. Other questions? Yes.
In this example here, in this very simple example, if you use different input for learning, would the weights and the value of the sigmoid bias, or how that is called, would they change, or would it always be the same at the end?
Okay, so the question is, you mean if I use a particular data set and I train it on this data set, maybe a very large data set, right? And then I erase that training, I wipe its memory, right? And I train it on another data set, then it's very likely to be different, yes, because it's trained up based upon that data. That's
Even in this very, very basic example, we only give only 2 inputs, a single hidden layer, and the whole function is perfectly deterministic.
So the question is, even on this very simple one, and the answer is yes, because it'll totally depend on the data that it's trained on, right? Okay. Other questions? Now, in this very, very, very simple one on XR, there are only 4 sets of data, right? And they're always the same. So, yeah, hopefully it'll always be the same, right? But you get any more complex than that, yeah, it'll be different.
Sorry, I just have a question.
Question? Yes.
Sigmoid function would never return 1 exactly, does it?
It would.
Okay. Repeat the question, please.
So the sigmoid function will never return 1 is the question. Technically not, because it converges, because of the nature of the function, it's only when you get close to infinity that you get to 1. So in reality, what you'd probably do is you'd round it up or down, or something within the programming language that you're using it will make that decision for you.
Great questions. Thank you. Okay, so the next topic that we're going to broach, I'm doing hand waving on this topic, and then Katharine will dive into it. But it's this thing called backpropagation. So the feed forward, there are actually 2 distinct things that happen with a neural network. One is you train it, and the other one is you use it to make predictions. So the training is where you're ingesting data, the data set into it, and you're training it on features versus labels, the classifications. And that training can take a while. That can take an order, seconds or minutes or whatever. But then the feed forward process of actually making a prediction using the weights it's been trained on, that's instantaneous. So we've just covered how you do feed forward. And now to make predictions and also as a part of the training. But the backpropagation, that's where the real magic is. That's where we're assessing what the weights and biases are for the various synapses and nodes of a network. And that we use something called backpropagation. Good luck explaining this one. Oh, by the way, here's a graph. When you train a neural network and you're training it on a data set, you do it iteratively. So you train, maybe going through a batch of the data set or maybe the whole data set if it's small. And so you're adjusting the weights and biases, and then you run through it again because it's iteratively getting closer to zero cost. And so in deep learning for J and TensorFlow and other packages, there's always some type of visual that lets you know that you're getting closer and closer to zero cost. So for example, in this particular data set and neural network that I was training, this was the graph that came out. So it came out with, after 600 iterations, it came out to where the score was 0.1, where it started out with 1. And so that's the kind of improvement you want to see, especially when you are kind of converging into almost a zero score. Now, take it away, Katharine.
So I'm going to do an injustice and slightly gloss over backpropagation when it comes to neural networks, because it's very complicated. So please talk to me afterwards and I can direct you either to my own knowledge or several resources. But basically what we've done now is we've walked forward through the network, and from our input, and we might randomly initialize these weights. So just randomly pick them, because we don't know what, the whole point is to find out what the best ones are. And we get our output, and then we're going to compare our output with what we know the right answer is. Now we need a way of changing these theta values to get closer to the right ones. And that is one of the big problems. That's the whole training. That's everything that you're doing. And if you get it wrong, it's a nightmare. I spent 3 days nearly crying to myself trying to make something work. So if you remember linear regression, if you came this morning when we're looking at house prices, and we've got this idea of the cost function, which you showed your graph before of the cost decreasing over time. And what we want to know is how do each of those theta values affect the output? How do each of them contribute to the answer that we're getting? So when we had like one input, so we just had the size in square feet, we can really easily see how changing the weight on that input affects the cost that we get. But now we've got 1, 2, 3, 4, 5, 6, 9-dimensional space. So now we've got the cost function according to 9 different variables. So that becomes really difficult, and I'm just going to explain it. I'm going to borrow an explanation from Andrew Ng from Stanford, where imagine you're on a hilly landscape. And this is just 3 dimensions, so you'll just have to go 9 dimensions in your head to scale it up. So you're on a hilly landscape, and what you want to do is you want to get to the bottom of the hills. So you take a step in the downward direction, and then you look around you and you go, okay, what's the next steepest step down? You take that step, and eventually you step down the landscape until you get to the bottom. If you've got a three-dimensional landscape where you just have one hill and one valley, it's really easy to find the right way to step down. But you might not have a simple landscape. You might have a landscape with mountains everywhere and hills everywhere. So you might not find the one deepest place. Because if you take all of these downward steps and you get to a deep place, you're not going to come back up again. And that's the problem with gradient descent. When we had one variable, we could see that the cost function over time changes a bit like a bow shape as the weight changes. So it's really easy to say, okay, there's one way down, there's one optimum, there's one point, there's one value where my cost function is the lowest. But when you've got 9 values, you might have one point where the cost function is pretty low, but another point over here where actually it's even lower, but you've taken these steps down, you're stuck there, because the gradient descent algorithm doesn't say, okay, now try going back up and then down another slope and back up and down another slope. So in reality, the principle of gradient descent is used, but you'll probably use a much more complicated optimization function to account for that. But yeah, these are the steps down the hill. The problem is your hill might not be simple, and your hill's in 9 dimensions. Yes?
So, as we have many hills and many valleys, basically, this is actually the reason why if you use different data, you will reach different values for the weight and for the sigmoid.
Yeah, the question is if you... Oh, I'm sorry. It was a really
It was
good
an
question.
assertion. It sounded like an
Yeah.
assertion, right? You're asserting that if you have different data sets, that it may be that the gradients are different, the locations of the hills and valleys and local minima.
Yeah, that's right. With different data, you have a different cost landscape, and you'll find different local minima. It's why there are several really important things to train. So in a way, the easy part is setting up your model, and the difficult part is how do you choose the data? Do you get more data or do you get more features? And that is optimization, which we'll come to shortly.
Very good. Thank you for the question. Okay, so now I'm going to switch over to a site. Actually, it's called Kaggle, and you may have seen that Google just bought Kaggle a few days ago. Kaggle is this great website for data scientists or machine learning enthusiasts, and it has lots of nice data sets, and it has contests and things like that. And so what I wanted to do when I was learning about machine learning, I wanted to play with the data set. And so I looked through them, and I found one that I thought would be kind of interesting on speed dating. And so this data set has actually many different features, many different columns in it, but I just picked 3 for input features. One was whether in the speed dating, basically you spend 2 minutes with a person, and then you decide whether you want to actually date that, go on a second date with that person. And so after their speed date, they would fill out a survey. And so 3 of the features were, did they feel that other person was attractive, intelligent, and fun? And so rate those on a scale of 1 to 10. And then say whether you would date again, 0 being no, 1 being yes. And so that's our data set. And so I created, using the DL4J library, I expressed a neural network. And so first, before showing that, walking through that code, I'll go ahead and run the example. So here's the speed dating example right here. And so we have a very small neural network, actually, only 4 neurons in the hidden layer. And as you would predict, 3 features and 2 labels, second date, no second date. And so so let's say that you think that someone is real attractive, 9, and maybe intelligent, 6, and fun. Let's make him 8. And so in that case, yeah, date again. But what's a really kind of eye-opening, maybe not so eye-opening, but in our society. It's kind of sad. With attractiveness at 9 and intelligence at 6, there's 81% that would do a second date. But if I reverse those, who thinks it would be lower? Right. And so I guess we think that attractiveness is more important than intelligence when deciding on a second date. But noticing now that that we've got the inputs, we've got the weights. We're doing one different thing here. We're normalizing the input, and that's a kind of a thing that we deal with when we optimize. But you want to normalize features so that one feature doesn't have too much weight, doesn't carry too much weight. And so we normalize them either between -1 and 1, or maybe 0 and 1, or around there. We try to make them so that the numeric values for different features are roughly in the same range. So here's the code then that configures that. We have a seed number. Remember, Katharine said that we randomize the weights. Well, the seed is what helps us randomize the weights. The iterations, the more iterations that you have, if you keep making improvement, the better you're going to, the lower you're going to get your cost function to a point, to some limit. And then your activation neurons, what are they going to be in the first layer, or actually by default? Learning rate, when you're stepping down the hill, the gradient, how big of steps do you want to take? If you're going down a hill, if it's a valley, if you take too big of steps, you're gonna skip the bottom, and then you're not going to converge on the lowest cost. And so here are the layers. Here's the input layer, where we have 3 and out and sending 4 out, and then here's the output layer where we've got 4 neurons coming in and 2 going out, and we're expressing that we want the softmax function. And so here is a way in deep learning for J in Java to express that. There's similar ways for TensorFlows. As a matter of fact, for TensorFlow, it's now in 1.0. It just got released about a couple of weeks ago, and there is this library on top called layers, in which you can express layers just kind of like we did here, where you're expressing the different layers. And this, by the way, in partial answer to your question about optimization, this is where if you, for example, your score is low by the time that you're done running your training, then you have some things to look at. Like, for example, this is a pretty low number of neurons in a hidden layer. It's a low number of layers, and maybe this is maybe I need more iterations, and so I could probably get this particular cost down to where the results are more accurate by changing those hyperparameters. Question.
So this normalization process, why those weights can't take care of that? Why normalization is important, and we cannot rely only on weights and neural network to optimize that maybe all at first given layer.
Okay, so the question is, why is it necessary to normalize the features inputs? Wouldn't the training, and optimizing, wouldn't that take care of it? And it's just that when you have different features of different ranges, then it can make it harder for the neural network to do proper training. Okay, I'm going to move on here. So we tried it, and yes, question.
Rather answer to that is more how computers count numbers. So if you deal with big numbers of multiplication and then you calculate on small numbers, then because you are using numbers with different scale and precision, then it's really easy to get, for instance, lost with these small numbers get lost because they won't be properly calculated. That's more numerical issue in calculation.
So your response is that it's more of a numerical issue in calculations.
If our computers were perfect in calculating to infinite, that wouldn't be a problem.
Okay. All right. So then this is just showing an output from training the speed dating data set after a given number of iterations and the scores. And then here we've got some information about not only the score, the cost, and how the cost function is going down, but also how they're classified. And so we can say in terms of how accurate it is, where we could take a test set of data that we didn't use with training, and we can then test this to see with the test when we did a feed forward a particular label, was it correctly classified by the model, and if so, how many times? So when I did the tests on this particular one, an example that was labeled as 0, which was no second date, it was correct that many times. But then, but it was incorrectly done this many times. And so the same thing with the yes answer. And so there's some scores down here that then model that. And we're out of time now, but if you went farther in the slides, you would see some slides that deal with what these numbers are in terms of precision and recall. There's also a link to a website. So we've got 3 minutes remaining, and I would like to know if you have any other questions for us. Oh, sorry, one more thing. The optimization information. If you go farther along in response to your question, there's this great resource for optimizing your neural network. And as you suspect, it's kind of a dark art right now, right? It's not cut and dried. Like, for example, a recent model that I trained, I had to try all sorts of different configurations, scaling up the number of hidden neurons in a hidden layer to 60 before it would kind of retain information and be able to bring the cost function down. Lots of different hyperparameters you can use, but in this article, and there's a link to it, it's got some good heuristics for what kinds of things to look for and to try first. Okay, now do you have any more questions? Yes, question.
The seeds that you specified, is it to start at random points to avoid the gradients to be in a certain position? Or what is the seed in your Java?
Okay, so the question is, what is the seed in the Java program? And so that's just a seed to seed a random number generator. And so that way, when we're generating the random numbers, it's going to be, if I seed it with a different number, it's going to put different random numbers in the model. And so it's just a way of putting in the random numbers and causing it to be different random numbers than maybe the last time you tried it.
So if you would use different seed numbers, could you avoid the problem that you mentioned, that you get stuck in a local optimum?
So if we seed with a different random number, or a different number, could we avoid the local optimization, the local minimum problem? And the answer is probably not, because those will generate very, very low random numbers, and it's just a way to keep them non-zero and random so that then the data set can be ingested. One more question, and then we'll go. Yes?
Can you use neuronal network to optimize complete mathematical problems? For example, scheduling. If I take a supercomputer and calculate my typical timetable problem, and then train a neuronal network with data, can I speed up the process?
I'm going to let you handle that one, and please repeat the question.
Can we use a neural network, see if I can remember this now, to solve mathematical problems? NP complete problems. I'm actually not sure. I'm sorry. I imagine that you can. I mean,
Maybe.
neural networks can solve mathematical problems. It would be down to how you most of the problem in getting a neural network to solve something is deciding how to input the data and the shape of it. I think Jarek might have an answer.
I'm going to give you the,
So
the
I'm
mic,
not expert in that, but
keep in mind keep in mind we have 20 seconds.
I absolutely not expert, but generally neural network is not algorithm that gives you exact answer. So it gives you some answer which is might be not correct. So generally, from mathematical point of view, it's not the way to solve any problems. That's not algorithm. That's a heuristic, basically. So it guesses something. In that case, if you accept this guess, that could be great hack, but it's not really, from mathematical point of view, correct. Yeah.
Thank you very much for your attention and for your great questions.